Hello, this is Professor Kuehn, and welcome back to my lectures on Einstein's theory of relativity. You might remember from reading Newton's Principia a few weeks ago, his definitions, Newton spoke of inertia. What was inertia? It was the tendency of an object to resist changes in its state of motion or its state of rest. So a dresser is hard to get moving even when it's on a slippery floor because it has inertia. Likewise, a moving dresser that's sliding across the floor is very hard to slow down. Why is that? Because once again, it has inertia. In fact, if someone were to try to slow it down, it would exert a force on the person that's trying to slow it. That is, a moving object exerts a force on an object that attempts to slow it down. Inertia is closely associated with the mass of an object. So the more massive an object, the bigger the force that it will exert on a target that tries to slow it down or to stop it. Now, what about light? For some time, there was some disagreement about whether light can exert a force on a target. Why is this? Well, because this would seem to imply that light itself has mass. Johannes Kepler, you might remember him as the astronomer and mathematician associated with the laws of planetary motion. Back in the 1600s, he argued that light could exert a force on comets. This is what he suggested was the reason why comets have tails. The light coming from the sun is pushing debris off of the comets and creating the tail. Nonetheless, the force is actually very difficult to measure. It wasn't measured successfully until about 1900 by a Russian physicist named Pyotr Lebedev. This phenomena where light exerts a force on an object that it strikes is now called radiation pressure. And since that time, it's been used extensively to carefully manipulate precisely the position and speed of atoms. And there's a Nobel Prize, I think it's in 2017 or 18, for something called optical tweezers, where scientists use laser light in order to carefully manipulate the locations of molecules. But does light really have mass? If it has inertia, then it would seem that it has mass. So let's try to address this question. There are a few ways to answer this question or to approach this question. And I want to address how does the theory of relativity approach the question of whether light has mass. Now, one way you might think about this is how one actually measures the mass of an object typically. Typically, in order to measure the mass of an object, you simply place it on a scale. Then you're measuring the force that gravity exerts on it, and you infer what mass it must have. This would be a measurement of the object's rest mass. And so we'll call this m with a 0 subscript, or m0. That would be the rest mass of an object, the mass that it would have when it's at rest compared to the scale on which it's being measured. The problem is you cannot stop light and put it on a scale. Einstein's theory of relativity claims that light does not have any rest mass. Nonetheless, it behaves as if it had mass because it has energy, and energy and mass are, in some sense, equivalent. This is the meaning of the famous formula that E equals mc squared. In other words, any object that has mass has energy associated with its mass even if it is sitting still. The amount of energy it has is given by the formula E equals mc squared. So what I'd like to do is I'd like to do an example of how you use this formula. This is an example of nuclear fusion. Then what I'll do is I'll come back and talk a bit more about this formula. So let's look at my sketchbook as I work through a nuclear fusion example. Nuclear fusion, an example of using the formula E equals mc squared. I want to talk about a specific nuclear reaction. You may or may not be familiar with writing down nuclear reactions. This might be your first introduction to it. That's okay. They look a bit like chemical reactions, but there are a few notable differences. So I'm going to write it down and then I'll talk about it. So let's take this formula, and I'll say what I mean by these in a moment. Okay, so on the left-hand side of this equation are the reactants, and on the right side are products. So you've probably seen things like this for chemical formulas. Note, however, what you have is two hydrogen atoms on the left-hand side, and on the right-hand side you have helium and a neutron. In other words, you're combining hydrogen atoms to produce a new atom, an atom of helium, plus a neutron. We have to be a little bit more careful. This right here is called deuterium. Why is that? Well, this here at the bottom left-hand corner is the atomic number, and the upper left-hand corner is the atomic mass. So this means that this hydrogen consists of one proton, but it has a weight of 2. That means it has a proton and a neutron in its nucleus. There's nothing said here about how many electrons there are. One could strip the electrons off and you'd still have the deuterium atom. Okay, the second atom here is called tritium. Tritium has also one proton, so it's hydrogen, but then because it has an atomic weight of 3, that implies that it has 2 neutrons in the nucleus. So you have deuterium and tritium, and those can react so as to produce helium. Helium is the atom having 2 protons in the nucleus. Since it has an atomic weight of 4, that means it has 2 neutrons. There are different isotopes of helium. There's helium-3 that just has 1 neutron, but here you have helium-4, which has 2 neutrons. And then over here, this implies, so this is helium-4 isotope. And then you have a neutron over here. That's denoted by there are 0 protons and it has an atomic weight of 1, so it's a neutron all by itself. So going into the reaction, we have 2 protons. That's on the left-hand side. So notice we have 2 protons coming out. And also, going into the reaction, we have 1, 2, 3 neutrons. And we have 3 neutrons going out because we have 2 neutrons associated with the helium isotope and 1 neutron that is being released also. Now let's introduce something called an atomic mass unit. So 1 atomic mass unit is given by the letter U, and it's 1.6605 times 10 to the minus 27 kilograms. Okay? And here's the point that I would like to make, and this is going to be the important point. So I'll kind of jump to the conclusion, then I'll do some calculations. So the mass of the reactants is going to end up being greater than the mass of the products. So the mass of the reactants is greater than the mass of the products. In other words, there is not conservation of mass in this nuclear reaction. Nonetheless, there is conservation of energy. Where does some of the mass go? The excess mass has turned into kinetic energy. So energy is conserved, but the mass of these objects going into the reaction is greater than the mass coming out, so the excess mass has gone into the kinetic energy of the products. So sum of the mass of the reactants shows up as kinetic energy of the products. And since kinetic energy is associated with motion and ultimately with heat, that is what causes the heat production in a nuclear fusion reaction. So let's do a few calculations here. So let's look at the reactants and their masses as one would measure them using mass spectroscopy. And we'll also look at the products and their masses. Okay, so what is the mass of your deuterium atom? Well, it's 2.014 atomic mass units. What is the mass, you can look these up, the mass of a tritium atom? Well, it's 3.016 atomic mass units. Remember, this is an atomic mass unit right here. It's about the mass of a proton. So what is the total mass of the reactants? Well, it's 5.030 atomic mass units. Well, what about the products? Well, we've got this helium isotope, helium-4. It has a mass of 4.003 atomic mass units. And then we've got a neutron, and its mass is 1.009 atomic mass units. So what is the total mass of the products? Well, it's 5.012 atomic mass units. So notice that the mass of the products is less than the mass of the reactants. So what is that difference in mass, and what does that correspond to in terms of difference in energy? So the difference in energy, I'll call that delta E, is the energy equivalent, using E equals mc squared, the energy equivalent of the difference in mass of the reactants and the products. Well, you could measure E, take this mass right here and multiply it by c squared to get the energy of the reactants, and you could take this mass right here, multiply by c squared and get the energy of the products, and subtract the two and you'll get the difference in energy. And so what I'm going to do is just write this as a difference in mass times c squared, which would be 5.030 atomic mass units minus 5.012 atomic mass units. Multiply that by c squared, and you'll get 2.69 times 10 to the minus 13th joules. So if you have one deuterium reacting with one tritium to produce a helium and a neutron, there will be a kinetic energy put out, that is the excess mass turned into energy of motion, of 2.69 times 10 to the minus 13 joules, which might seem like a very small amount of energy, and it is, but the point is that this is for a single reaction of a single deuterium, single tritium, producing a single helium and a single neutron. What if we had 1 mole of reactants? For 1 mole of reactants, what would you do? You'd multiply this by 6.02 times 10 to the 23rd, which is Avogadro's number, and that will give you 18 times 10 to the 10th joules. Now that's a really big number. How big is that? Well, by comparison, you might think about it this way. If you were to react just 1 mole of dynamite, TNT, so 1 mole of TNT, how much energy would this produce through those chemical reactions? It would be about 10 to the 4th joules. So this is a factor of 1,000,000, at least 1,000,000, more than 1,000,000 larger than an equivalent reaction of TNT. So a nuclear fusion reaction creates over 1,000,000 times more energy than an equivalent mass chemical reactions, and this is precisely what makes nuclear reactions very efficient in producing power. I'll stop there and we'll come back and talk more about Einstein's theory of relativity in my next lecture.